All right, hello everyone, and welcome to the Lecture 5 R tutorial. So today we're going to be covering a workhorse model of data analysis, which is multiple regression. So we'll have talked about what this entails in class. In RStudio, it's really not going to mean that much extra in terms of commands. In terms of running the model, it's going to look very similar to the single variable regression. But we're also going to discuss today how to present multiple regression results in a way that I'm going to be expecting to see on your final group projects. And that will require another package. So now we've got quite a collection of packages. So we're going to have tidyverse as usual. We're going to have a ggplot. We have our two packages which are required for doing robust standard errors. And now the last package we're going to need is called Stargazer. Stargazer is a package for presenting summaries of regression output and also summaries of data tables, which I won't talk about today, but which you can feel free to ask me about and which I'll definitely cover before you have to write up your projects, because summarizing your data very quickly and easily is something that R can do for you. So just to recall, if you need to install a new package, you're going to go to packages, you'll go install, you'll search for the name of the package here, Stargazer. You'll click the package name, you'll click install. And then once you've done that, you'll want to attach it either by clicking the check mark next to the name or running this kind of command here. Okay, so we'll run all of these things. Okay. And for this week, the data set that we're going to be using is the same one we used in the homework 3 assignment. So you'll kind of find where you put that. And once you've done that, and so actually let's do it. Let's kind of shake the rust off a little bit. Remember, if you want to import a data set, you can do it from here. You're going to want to do read R. And then you'll browse. You'll find wherever you stored it. Okay, and then you can do import, right? Here it's showing a preview of what the data looks like. So you can do import, or all you really need is this command here if you want to just have it as a line in your code that you can run. So, okay, there we have homework 3 data. As usual, we will check for outliers. Or sorry, we'll check for missing data. So filter homework 3 data with complete cases and run that. And as we know, with this data set, there are no missing observations or missing variables for any observations. So we have a complete data set. Okay, so when we look at our data, before what we did was we ran a regression of income on experience. And we looked at the effect of increasing experience by 1 year on your income level, right? And we broke our sample into 2 and we kind of did some stuff there, but it was always single variable. So now we can run a multivariable regression. So to do that, it's super simple. What we'll do is use our same LM command. Income is going to be our left-hand side variable. And then experience is one of our right-hand side variables. So maybe let's just start with that. Or actually, no, let's add something in here. So to create a multiple regression formula, you just do a plus sign and add on another variable, right? So what else do we have? We have college and we have geography. So why don't we just throw everything in there? That's all the variables in our data set. And the data that we want to use is DAT. Okay, so let's run this. It's going to be stored in the upper right as usual. And what can we do to kind of take a look at it? Well, we have a few options, right? So summarize was one option. Sorry, summary. So summary. When we run that, we can see in the console some information. So we see a few interesting things, right? We see experience here. So what is this number? This is the effect of increasing experience by 1 year on average income, holding fixed whether or not you went to college and which province you live in. Now, recall from lecture, when I say holding fixed, it doesn't matter what value we hold those things fixed at. Right? The effect of experience is always an extra $1,000, regardless of what the value of the other variables are. They're just being held fixed, whatever they are, right? So experience goes up by 1 year, income goes up by $1,026, okay? Good. So when we look at these other variables, we see here college. So college is a Bernoulli variable, taking values of 0 or 1, 1 if you've gone to college. And we can see people who go to college, when we increase college by 1, that's someone who didn't go compared to someone who did go. That person who did go, their average income would increase by about $4,019, right? And that's holding everything else fixed once again, right? So for two people who look identical in every respect, except one went to college and the other did not, our regression output is going to say that they made an extra $4,019 as a result of going to college, right? So we're kind of interpreting these coefficients as causal under the assumption that we've controlled for everything that matters for determining income, right? So there's nothing in the background here that's leading to selection bias or omitted variable bias, okay? So that's interpreting college, our Bernoulli variable. And then what do we have here? We have some things that we don't actually have in our data set. What is geog BC? That's not a variable that we included here. You can see in our regression, we only included geog, right? Because geog is a variable that's in our data set. But it takes these different values, A, B, O, N, Q, C, and presumably BC, okay? So we can verify that we kind of have 4 different values for geography with a ggplot, right? So we can do a geom bar with the aesthetic is x is equal to geog, right? Good, so there we can see in the bottom right now, just a raw count histogram. We have 4 values: Alberta, British Columbia, Ontario, and Quebec for the different provinces. Most people in our data set live in Ontario. These seem to kind of roughly follow population, although Quebec seems to be a little bit underrepresented. And maybe Alberta is overrepresented. Okay, so we have 4 values of geog. Geog does not take numeric values. It takes these categories. This is a categorical variable. So we entered in a categorical variable into our multiple regression formula. And what R did with that is it turned the categorical variable into dummy variables, right? So it generated 3 dummy variables: British Columbia, Ontario, and Quebec, okay? We have 4 categories. So remember, because of the dummy variable trap, we're going to generate 3 dummy variables to represent those 4 categories, okay? And each of these dummy variables, you can interpret as if it's just a Bernoulli variable. So this one is the effect of living in British Columbia is, holding everything else equal, decreases your income by about $4,000 on average, right? $3,997, okay? The effect of living in Ontario decreases your income by about $2,034, and so on for Quebec, okay? So that's how we're interpreting the coefficients. Now, what happened to Alberta? So Alberta got excluded because with 4 categories, we're going to have 3 dummy variables, and then our intercept captures the baseline effect. So our intercept is kind of corresponding to someone in Alberta, right? Because if we set all the dummy variables equal to 0, right? If you don't live in BC, so this is equal to 0. And if you don't live in Ontario, so this is equal to 0. And you don't live in Quebec, so this is equal to 0. Well, then you must live in Alberta, right? Because everyone in our data set lives in one of those 4 provinces. And if you live in Alberta, that's saying that on average, you're making about $32,000. BC then when we look at this coefficient, we can also interpret it as the relative difference from kind of someone who lives in Alberta compared to BC. So if you go to BC, holding everything else equal, your income should be expected to drop about $4,000 relative to being in Alberta, right? So all of these coefficients on the dummy variables for the province categorical variable represent kind of relative to the baseline category, relative to the excluded category, which here is Alberta. When we have a variable that looks like this with text in our data set, R will automatically treat it as a categorical variable. So it will automatically generate dummies and run the regression with those dummies. When this is not a categorical variable, when this is a numeric variable, but it represents categories, we need to take an extra step, right? So if instead of these names, geog was coded as 1 for Alberta, 2 for Ontario, 3 for Quebec, 4 for British Columbia, if you just try to run the regression, R will interpret those just as numbers, right? Okay, oh, here's a continuous or discrete numeric variable. And it'll give you one coefficient, which is the effect of increasing that variable by 1 unit, which is nonsense, right? There's no reason why the effect of going from Alberta to Ontario should be the same as going from Ontario to Quebec, right? 1 to 2, 2 to 3, our regression will say that those have the same effect on income, but we know that that is a silly thing to try to be modeling. So instead, you'll need to convert your variable to a factor, right? And we know how to do that. So if we wanted to create a new variable, geogfac, for geogfactor, we would just do as.factor geog, okay? So we don't need to do that here, but in your homework, you will need to do that because state ID is in fact a numeric variable, right? So you're going to want to use that factorized version of the categorical variable when you do the regression in your homework, okay? If we do it here, then we'll see that there should be no difference except that the name of the variable in our summary table looks slightly different. Right now it's geogfac BC, but the coefficients are identical to what they were before. Okay, perfect. So that's interpretation. Recall with standard errors, we don't actually have the correct standard errors using the summary command. With the summary command, we have our homoscedastic standard errors. What we would like are heteroscedastic standard errors. So how do we adapt our coef test for the regression with multiple variables? It adapts itself. So we can just put in reg1 and vcov equals vcov heteroscedasticity consistent. That's the HC. And then we have reg1. Okay. So we run that and we can see the t values have gone down slightly, but they're still quite large, right? In this case, it went up, so it's interesting. Sometimes it happens, but in all cases, right, we were very, very significant before. We're still very, very significant. So heteroscedasticity doesn't seem to be an issue here. Just because it hasn't really been an issue so far, though, doesn't mean we don't need to pay attention to it. So we definitely do need to pay attention. Okay. Cool. So we can interpret our t values and our p values exactly the same with our coef test, right? We can see that, say for one of these, the probability of observing a coefficient as large as 1026 for the exp variable under a null where it has no effect is less than 2.2 e to the negative 16, right? So the probability is basically 0 that we observe something this large in a randomly drawn sample if the true effect of experience is 0. So we can definitely safely reject the null that the effect of experience is 0 in this data set. Okay. Perfect. So what else do you want to do? That's kind of it for running a regression and interpreting a regression, the last bit is presenting a regression. So one thing that I'll ask you to do in the homework is to kind of present two regressions alongside each other using the Stargazer command. The first regression I ask you to present is just kind of a basic single regression, single variable. So we'll do kind of one of those here. So reg0, this is just regressing income on experience, right? So a basic regression. Okay. Now with Stargazer, this will allow us to look at both of these regressions together. So all you need to do is list out the regressions that you've run and then enter type equals text. Otherwise, it's going to default to a format of output, which is not so good for reading by humans. If you are compiling your output using LaTeX, then the default is LaTeX code. So you can basically copy paste Stargazer's output directly into your LaTeX compiler. But if you're not using LaTeX, then you're going to want to use just type equals text. So let's run our reg0 and let's run Stargazer. Okay. And so what we have here is a very nicely formatted table of regression output. And what we can see is reg0 was our first regression that we reported, and reg1 is our second regression that we reported. And so we have column 1, that's going to be reg0, and column 2, that'll be reg1. And we can see that here's the effective experience. That's the estimated coefficient. Here's the standard error. Here's the significance, 3 stars. That's going to mean p less than 0.01. We have the number of observations at the very bottom. We have the R squared being reported. And then we have some other stuff which I haven't really told you about, but which you can just leave there for now. With regression 2, now we can see, or with column 2, we've run regression 1 here, and you can see all the coefficients that have been reported from our summary, right? But now they're all reported here. So one thing that's really nice about Stargazer output is that you can compare across columns what changes as you start to add in more controls. So most of you are going to be doing multiple regressions for your projects. So one discussion I'll want to see is as you add in more controls, you should be minimizing the effect of omitted variable bias, right? And you may even want to discuss, does your estimated coefficient on the variable that you care about change in the direction that you would expect given the relationship between that variable and the omitted variable, okay? Which will make sense after if you've already been to lecture. If you're watching this before lecture, just wait and see, okay? So that's our regression output with Stargazer. The one bad thing here is that Stargazer will default to the homoscedastic errors, okay? So we're going to need to force it to, we'll need to feed it the heteroscedastic errors as kind of a separate argument, okay? So the separate argument is going to be SE for standard errors. And what we need to do is kind of generate, or we need to recover these heteroscedastically robust standard errors. So the way that we do that is let's kind of create 2 new variables to store the standard errors in. So robust standard errors for regression 0. Here's what this looks like. So this you recognize vcov HC. That's saying like the heteroscedasticity robust standard errors for reg0, okay? Diag. So sorry, these are actually the variances. These are not the standard errors. So that's where the square root comes in. You're going to want to square root it to get it back to standard errors. The diag I'll show you in a second, but when we run this, what we see are kind of the standard errors for the intercept and for EXP, but now they're heteroscedasticity robust, right? For regression 1, same thing. Okay. Now, when we just run vcov hc reg1, here's what we get. It's a matrix. What is this matrix? So this is kind of for personal interest. You don't need to know this to just kind of run these commands and feed the standard errors into Stargazer. This matrix is on the diagonal. It's the variance of each of the estimated coefficients. So when we do diag, we recover all the diagonal elements of this matrix, square root them. Those are the standard errors. What about the off diagonal? Off diagonal is the correlation, sorry, it's the covariance between each of these row variables and the column variables, right? So it says that the covariance between EXP and college is positive. The covariance between EXP and living in BC is negative, okay? So these are all, this is the variance covariance matrix. That's what VCov is, variance covariance, okay? Don't need to know that, just need to recover the robust standard errors. And then we'll add these to our list of standard errors, making sure that the order in which we enter them corresponds to the order in which we entered the regressions that they correspond to. So reg 0 is our first regression. So first element in this list, RSE for reg 0. Reg 1 is our second element in the SE list, RSE reg 1. Run this. And this is going to be our kind of heteroscedasticity robust standard errors. Okay, perfect. So that is it for this week. That's running the multiple regression, interpreting the output of our multiple regression, and then summarizing it for presentation. One last note, when you run this, so to get this into your homework, you're just going to want to select it and do a copy paste, right? To get it so that it looks this nice in your Word document, because it won't when you copy it for the first time, what you're going to want to use is what's called a monospace font. Okay, monospace font is each letter and each space has the exact same spacing associated with it, which is what we see in this output, right? It looks kind of this kind of typewriter font. So you're going to want to use like a typewriter font, which you can Google. I think Courier might be a typewriter style font, but Google that, Google monospace font or typewriter font, pick whichever one you like the best. And for just the table, make sure that the font is set to that monospace font, okay? All right, okay, so now that is it. Done for this week's R tutorial. So I will see you guys in class. I'll see you guys in office hours. Yeah, good luck with the coming week. See you.